Our next example of an application of Newton's second law is what we call the Atwood machine. In actuality, it's just a simple pulley. And here we have a pulley, one string, two masses connected to it, one bigger than the other, and of course you can see that there's going to be an acceleration. The heavy mass is going to be accelerating downward, the lighter mass is going to be accelerating upward. What is the acceleration of the system? And what is the tension on the strings? And of course, again, if the pulley has no mass and no friction, you would expect T1 and T2 to be the same, which in this case it is. All right, let's draw all the forces acting on the system. So again, I'm going to find the acceleration by looking at this as a singular system right here. We have M1G pulling down in this direction, and we have M2G pulling down in this direction. Now, which is bigger? M1G is bigger, and since everything is connected, you would expect the whole system to be accelerating this way. So I'm going to call acceleration in this direction as the positive direction. And then this force would be aiding the acceleration, same direction of acceleration. This force would be opposing the acceleration because it's the opposite direction of acceleration. And of course, using Newton's second law, we can write F net equals mass total times acceleration. The net force then of course would be M1G, which aids the acceleration, minus M2G, which opposes the acceleration, equals the total mass M1 plus M2 times the acceleration. And of course at this point, if we divide both sides by M1 plus M2, we have the equation for the acceleration of the Atwood machine. Now let's plug in the numbers. So M1 is 10, G 9.8, minus M2, which is 5, times G 9.8, all divided by M1 plus M2, which is 10 plus 5. And of course, the units are going to be meters per second squared. This is the acceleration. And let's see here, we have 49 divided by 15, which would be 3.27 meters per second squared. So acceleration equals 3.27 meters per second squared. All right, now to show, for one, that tension 1 will equal tension 2, and to show how easy it is to apply this concept of how to calculate the tension of the string on both sides of this pulley, let's start with tension 1 first. And here we can see that since mass 1 is being accelerated downward, we can say that tension 1 is equal to the weight of that object, M1G, minus M1A, because it's accelerating downward. To find tension 2, we can say that it's equal to the weight of this object, which is M2G. But since M2 is being accelerated upward, we have to write plus M2A. And those should be equal to each other. So let's plug in the numbers and find out. So this is equal to 10 times 9.8 minus 10 times 3.27. And here, tension 2 is going to be 5 times 9.8 plus 5 times 3.27. All right, so the tension will be 98 minus 32.7, which will be 65.3. And here, that will be 49 plus 5 times 3.27, and we get 65.3. And you can see how nice and easy it is to use that concept to find the tension of the string. Just simply take the weight of the object that is suspended from it, plus or minus the force required to accelerate it, plus when it's accelerated upward, minus when it's being accelerated downward. Okay, and that's how you do the Atwood machine.